All right, hello, welcome to this week's Math 2414 weekly review. This week we're going to be covering section 11.4, which is comparison tests, and section 11.5, which is the alternating series test. All right, so let's go ahead and get started with section 11.4. So the first thing we're going to cover in section 11.4 is going to be the direct comparison test. So under the direct comparison test, the first thing we have to do is we have to make sure that both A and B are series of positive terms. So as long as that's satisfied, the direct comparison test states that either states that in one scenario, if B is convergent, and A is less than B for all n, then series A is also convergent. It also states that if series B is divergent and A is greater than B for all n, then series A also has to be divergent. So let's actually go ahead and visualize this, because I mean this one is actually pretty much just common sense, is mostly common sense. There is an actual mathematical way to do it, but honestly, visually, it just makes more sense. So for example, if we have series A is the blue line, and then B is the red line. And this is sort of something similar to what we talked about, I believe, when we did improper integrals as well. So for example, if we have B, and then we have A below it, and we know that B is going to equal some number L, well then A has to be less than B. So therefore, that has to be less than L. Therefore, if B is equal to a constant, then A also has to be a constant. Similarly, if A is our bigger series, and we have B down here, and B is equal to infinity, then A also has to be bigger than that infinity. So A is just a bigger infinity than B. But let's say we have a situation where we have something like this. A is our smaller series, and B is our bigger one. And we know that B is equal to infinity. Well, that actually doesn't tell us anything about A. A could be a constant, or A could just be a smaller infinity. That doesn't tell us anything, so therefore we have to make sure that follows these two scenarios. Because if it follows this scenario, that doesn't tell us anything. Or if we have a situation where A is bigger and B is smaller, and B is equal to some constant, that tells us nothing about A. A could be infinity, or it could be a bigger constant. So now let's go ahead and try some examples. So for all of these, we just want to know whether or not they converge or diverge. So for the first one, we have our series, of course, from 1 to infinity, and it's going to be n minus 1 over n cubed plus 1. All right, so we're going to have to actually play around with this, since right now this isn't a super obvious series that we could do. Yes, there's maybe integral tests, but this also isn't a very pretty one to integrate. So let's go ahead and just try to play with this a little bit. So we have n minus 1 over n cubed plus 1. Well, let's say we wanted to get rid of that minus 1 in the numerator. Then n over n cubed plus 1 has to be bigger than n minus 1 because our because our numerator is bigger now, and our denominator is the same. And now let's say we want to get rid of that plus 1 in the denominator. Well, our function is still bigger because now we made our denominator smaller, which makes the full thing bigger. So therefore, we now have something that we can compare with. We can say for sure, and then since we know n over n cubed is going to be equal to 1 over n squared, we can go ahead and compare this, our initial series, to the series of 1 over n squared. So we know from our P series that 1 over n squared is convergent. So if 1 over n squared is bigger than n minus 1 over n cubed plus 1, and 1 over n squared is convergent, therefore our initial series also has to be convergent. All right, let's go ahead and try another one. All right, so in this one we're going to go ahead and have our series, and it's going to be 9 to the n over 3 plus 10 to the n. All right, so let's look and see if there's anything we can go ahead and do with that. We can see that this looks fairly similar to a geometric series, as it has a 9 to an n over 10 to the n, but we have that 3 in the way. So let's go ahead and see and try to get rid of our 3. So if we get rid of our 3, 9 over n over 10 to the n is going to be greater than our initial series, because once again we made our denominator smaller, making the full thing bigger. Now we are left with having our series of 9 over 10 to the n, which could also be written as 9 over 10 times 9 over 10 to the n minus 1, giving us the form of a geometric series. Because this is the bigger series, we test for convergence. So we're going to go ahead and see. We know that 9 over 10 is less than 1. Therefore, this series is convergent. So that makes this series convergent as well. All right, so let's go ahead and try one more example with our direct comparison test. So for this one, our series is going to be n plus 1 over n square root of n. All right, so we're going to go ahead and let's see if we can find something to compare it with that's easy to work with. So what we can try to do is let's get rid of that 1, that n plus 1. So if we do that, n over n square root of n is going to be smaller than n plus 1 over n square root of n. Because now we made our numerator smaller, therefore our full thing will be smaller. But so now what we need to do is we can go ahead and test for divergence with this piece. So we can go ahead and convert this to 1 over square root of n, or 1 over n to the 1/2. Well, by our p series, this is going to go ahead and diverge. So because our smaller series diverges, our initial series will diverge as well. So this is overall simple enough. I mean, it's just trying to find something easy to compare with. And usually with comparison tests, both with direct comparison and with limit comparison, which we're going to talk about next, the easiest thing to do is usually trying to get into a form of either a p-series or a geometric series, mainly just because those are going to be the ones that are most obvious whether or not they converge or diverge. So now let's actually go ahead and move on and talk about limit comparison test. So in some cases, if we use our direct comparison test, we can sometimes end up getting, we didn't have it in any of these examples, but you could get stuck in a situation like one of these two scenarios. So where maybe your bigger function is infinity, or maybe your smaller function converges, and that doesn't tell us anything about the other. So in order for us to kind of bypass, figure out a way around this, we have what is called the limit comparison test. All right, so for our limit comparison test, we still kind of have the same stipulations. We have series A and series B, of course, are both series with positive terms. So if we get a form such as the limit as n approaches infinity of a to the n over b to the n is equal to c, and c is a finite number and is greater than 0, then both series converge or both series diverge. And that also makes sense because, for example, if one converged and one diverged, there'd be no way we can get a finite limit that is greater than 0. But, for example, if we think about L'Hopital's rule, so let's say they both diverge. If we think about L'Hopital's rule, usually we can rework that to where we can get some sort of finite number. Now, in that case, it may be 0, it may be infinity, but usually we can get something to cancel out. Or, of course, if we just have two converging, we just get a finite number over a finite number. So let's go ahead and do a few examples with these as well. All right, so once again, we're just going to go ahead and we just want to know whether or not our series converge or diverge. So for our first one, we have n squared plus n plus 1 over n to the 4th plus n squared. So if we have some polynomials in here, maybe it wouldn't be a bad idea to first try to factor it. So if we try to factor it, our numerator does not factor. However, our denominator does. We can pull out an n squared to leave us with an n squared plus and an n squared plus 1. The thing is, though, that doesn't really help us if we can't cancel anything out. So what we're going to have to do is we can go ahead and try to use our limit comparison test to figure something out. So what we can do is, so we see that we have an n squared on the bottom. So in order for us to maybe try to play with this, we need to either try to put an n squared on the top or get rid of the n squared on the bottom. So let's go ahead and let our a sub n be our initial series, or our initial sequence in this case. And we're going to go ahead and let b sub n be 1 over n squared. And we know that that one is going to converge due to the p series test. So if we do our a sub n over b sub n, we are going to get n squared plus n plus 1 over n to the 4th plus n squared over 1 over n squared. Well, we said earlier that this denominator could actually be written as n squared times n squared plus 1. Well, we can go ahead and get rid of these 1 over n squareds and let those cancel out. So therefore, we are left with a to the n over b to the n is equal to n squared plus n plus 1 over n squared plus 1. All right, so now we can go ahead and take the limit of that. So whenever we do this, we can either have two ways. We can just plug it in, get infinity over infinity, or do L'Hopital and do L'Hopital's rule. Or in this case, since we'd have to do it twice, we can just divide. We can just multiply times 1 over n squared on both the numerator and denominator to get us 1 plus 1 over n plus 1 over n squared over 1 plus 1 over n squared, which is equal to 1 plus 0 over 1 plus 0, which is of course going to equal 1. Well, 1 is a finite number greater than 0, and we know that our B series converges. Therefore, this series has to converge as well. All right, let's try another one. All right, in this one, we are going to have n plus 3 to the n over n plus 2 to the n. Now, on paper, so if we first look at this, we can think, oh, we can just do a direct comparison test and get rid of those plus n's. The thing is, though, is we can't say for sure whether 3 to the n over 2 to the n is bigger or smaller than our initial series, because we're taking away from our numerator, which would make it smaller, but we're also taking away from our denominator, which would make it bigger. So therefore, we can't say for sure which one to do. But what we can do is we can actually go ahead and maybe play with our limit comparison test. To maybe see if we can simplify this to something that we can't actually work with. So let's go ahead and let our a sub n be our initial sequence. Now, since we're kind of in a form of a geometric series, let's go ahead and pick our b sub n to be something that is as well. So let's go ahead and do, so we're going to go ahead and do 3 to the n over 2 to the n. That way, whenever we flip it, and that way, whenever we divide, we can maybe cancel out that 3 to the n and cancel out the 2 to the n's. And of course, for this is equal to 3 over 2 to the n, which we know would diverge due to our geometric series test. So let's go ahead and see what we get. Our a to the n over b to the n is going to be n plus 3n over n plus 2 to the n. We're going to divide, so I'm just going to flip the, multiply times the reciprocal and get 2 to the n over 3 to the n. So if we go ahead and cross multiply, we're going to get n plus 3 to the n over 3 to the n times 2 to the n over n plus 2 to the n. So now we need to go ahead and take our limit. So just looking at this, I think it's going to be easier if we go ahead and do these each separately and then multiply at the end. So let's go and then multiply and just check and see if we get an actual finite positive number. All right, so now let's go ahead and play with this. So let's go and take our limit as n approaches infinity of n plus 3 to the n over 3 to the n. We can go ahead and split this up, so we can actually go ahead and get n over 3 to the n plus 3 over 3 to the n. That this 3 to the n over 3 to the n will cancel out to 1. So now we can just take our limit. If we take our limit of this n over 3 to the n, we're going to get infinity over infinity. But we can go ahead and do L'Hopital's rule with this one to get us the limit as it n approaches infinity to get us 1 over the derivative of 3 to the n. I know we don't typically use that one, this particular rule, a ton, but that one is also, it's based similar to our normal like e to the x rule, and that one will get us natural log of 3 times 3 to the n. So therefore, we're going to get 1 over infinity, which is 0. And then, of course, we had our 1 over there, so a plus. So therefore, this section will have a limit of 1 because we had a 0 and then a plus 1. So now let's go ahead and take our other one. So if we do this, once again, we're going to get infinity over infinity. So what we can, but we can either, once again, we can either do L'Hopital's rule with this, but we can try L'Hopital's, but the issue with that is we're going to kind of end up kind of back to where we started, or actually, let's go play with it. You can, okay, you can either do L'Hopital's rule, and you can try with that, or you can divide. Since we have a 2 to the n in both, we can kind of do what we did earlier and do 1 over 2 to the n. That's the way I did it on this, but then just thinking, I was like, you can also try L'Hopital's rule if you're doing this at home and see if you get the same thing. So if we do this, we're going to get the limit as n approaches infinity of 1 over wait, give me just a second. Okay, give me just a second. Yeah, I just realized I had a math mistake on there. No big deal. But what we can do is, yeah, we can go and do n over, yeah, we can go and do n over 2 to the n plus, plus 1. Let's go ahead and take our small limit as that n approaches infinity of n over 2 to the n, because that's going to give us an indeterminate form. So therefore, we're going to go ahead and get actually, yeah, go ahead. Let's go back. Let's go back and do L'Hopital's from the beginning. So yeah, we're going to, up here, we're going to get natural log of 2 times 2 to the n over 1 plus natural log of 2 times 2 to the n. We're still going to get infinity over infinity. All right, so we're just going to do this again. We're going to get 2 natural log of 2 times 2 to the n. That one's going to go away, so 2 natural log of 2 times 2 to the n. That's going to cancel out. This is going to cancel out, so then we're just going to be left with 1 for our limit. All right, so therefore, we're going to get a 1 right here. So therefore, our limit as n approaches infinity of a to the n over b to the n is equal to 1 times 1, so 1. So therefore, that fulfills our criteria, and we know that our b to the n is divergent. Therefore, our a to the n also has to be divergent. All right, so let's go ahead and also touch on estimating sums. So we never actually really got to do a section 11.3 weekly review due to the exam, but I can go ahead and touch on some stuff, just kind of do a brief touch up on what they talked about in that one. That way we can actually proceed with this part of 11.4. So estimating sums. Yeah, and this one, I'm just going to put, we have a little bit of 11.3 mixed in with our 11.4. So because we're doing limit comparison tests, we're actually working with two series. We have our series A and we have our series B. And what we can do is we can say for series A that our remainder, or R sub n, is equal to our sum minus our partial sum, which is going to be equal to a to the n plus 1, a to the n plus 1 plus a to the n plus 2 plus a to the n plus 3, and so on and so forth. That part isn't like super important, but really we need to mainly just pay attention to this. Now with our b, we can also say our remainder for b, which we're going to call t sub n, or big T, is equal to our sum of b minus our partial sum of b. And it kind of follows the same thing, b, and so where we have b sub n plus 1, b sub n plus 2, b sub n plus 3, and so on and so forth. So whenever we're working with limit comparison tests and estimating sums, essentially what we can say is, let me go and switch colors. If a sub n is less than or equal to b sub n, then r has to be less than or equal to t. So now let's figure out what we can do if we know our b. So because usually we know our b, we need to figure out our a, is usually what we work with when we're doing comparison tests. So usually, like I said earlier, whenever we do comparison test, we usually set b to be either a p-series or a geometric series. So that's going to actually kind of depend on how we do our sum and our remainder. So if B is a p-series, we can state that the integral of n plus 1 to infinity of our function is less than or equal to our remainder t, which is less than or equal to our integral from n to infinity of f of x dx. And if they want us to find our actual sum of t, what we can do is we can also say that our partial series t, or our partial sum, plus the integral from n plus 1 to infinity is less than or equal to our sum t, which is less than or equal to our n to infinity f of x dx plus our partial sum. If you kind of want to go read more about this, I would definitely check your book, check your prof's videos and your notes. Because like I said, we didn't really get a chance to go over that in our review session. But this is essentially the process you're going to use whenever B is a P series. But if B is a geometric series, then we can say that our remainder is just going to be the sum of the geometric. And we also know that R is going to be less than or equal to T. I don't think you'll really get that many problems messing with estimating with geometric series. I didn't see any example problems in your book, or at least not any that like had a process shown in your book. But I would also just double check with your profs to see if they need you to know that or not. But we're going to go ahead and do an example. Just kind of working with this a little bit. So what we want to do is use the first 10 terms to approximate the sum and find the error of that approximation. And our series that we're going to have is going to be 1 over 5 plus n to the 5th. So if we go ahead and do our limit comparison, we know that's not one we can easily integrate and work with. So we're going to have to find a series that we can actually work with. So one that we can use is 1 over n to the 5th, which is going to be bigger. So therefore, we can say we know that R is going to be greater than or equal to T. So we know that this is connected to R, and this is T. So therefore, we can say that our error of R is going to be smaller than our error of T, which is going to be smaller than our integral from 10, since that's our starting point. They want us to use our first 10 terms to infinity of 1 over x to the 5th, since that's going to be like our b sub n dx. So if we go ahead, we integrate that, we're going to get our limit. Let me go and switch colors actually. Our limit as t approaches infinity of the integral of 10 to t 1 over x to the 5th dx. That is going to be the limit as t approaches infinity of negative 1 over 4 x to the 4th from 10 to t. We're going to get limit as t approaches infinity, negative 1 over 4 t to the 4th minus a negative 1 over 4 times 10 to the 4th. And then, of course, that's going to go cancel out. If we do our limit as t approaches infinity, this is going to cancel out to 0, since we're going to get 1 over infinity. So then, therefore, we know that our error for our r sub n has to be smaller then 1 over 4 times 10 to the 4th, or 1 over 40,000. So we found our error, and now for our sum, they just wanted us to do a partial sum for this. So what we're going to do is just plug in our first 10 terms. So 5 plus 1 to the 5th plus 1 over 5 plus 2 to the 5th, 1 over 5 plus 3 to the 5th, and then you're just going to kind of keep going until you get all the way to 5 plus 1 over 5 plus 10 to the 5th. And that's going to be your final answer. All right, so our next section is going to be section 11.5. Which is alternating series. All right, so just as a quick definition, alternating series will go between, they go between, or like back and forth between positive and negative terms. And when you see them, they will usually have either a -1 to the n minus 1 or like a -1 to the n somewhere in there. So now we have our alternating series test. So it states if we have an alternating series and it satisfies these two criteria, the first being that b to the n, b sub n plus 1 is less than b to the n for all n. Or in better terms, like if the absolute value shows that it's decreasing, and that our limit as n approaches infinity of our b sub n, or in better words, our absolute value is equal to 0. Then the series is convergent. So let's go ahead and do some examples with this. All right, so once again, all of these are just going to be, are they convergent or are they divergent? So the first one we have is we get 1 over natural log of 3 minus 1 over natural log of 4 plus 1 over natural log of 5 minus 1 over natural log of 6 plus 1 over natural log of 7, and then we're just going to kind of keep going through that pattern. So the first thing that we need to do is we need to go ahead and come up with a series for this. So we can see we're flipping back and forth, so it is going to be an alternating series. So we have a couple options. We can go ahead and start with n equals 1 or n equals 3. Either way works. Let's go ahead and start with, let's do n equals 3, just to make things a little bit easier. All right, so we know we're going to have a -1, and we know that we are starting off with it being positive, so let's do an n minus 1, since that's going to get us a positive for our first term, times 1 over the natural log of n. You could also rewrite this as by starting from 1 and doing -1 to the n minus 1 of 1 over natural log of n plus 2. Either way works. Let's actually go ahead and do this second one. All right, so let's go ahead and first things first is we need to go ahead and check our criteria. So is this decreasing? So we can see that if we take the absolute value, the denominator is going to get bigger and bigger and bigger with each term we get, while the numerator is constant. So therefore, we can say that, yes, it is decreasing. So now we have to just check our limit as n approaches infinity when we have the absolute value. So the limit as n approaches infinity of 1 over natural log of n plus 2 is approximately 1 over natural log of infinity, so 0. So therefore, our second criteria is met. Therefore, we can say that this series converges. All right, so let's go ahead and do our next one. All right, so for this one, our series, we're going to have -1 to the n times n squared over n squared plus n plus 1. All right, so we need to go ahead and see if it's decreasing. So we have a couple ways we can do that. One way, we can either graph it, we can plug in n plus 1 and see if that changes anything, or we can just kind of think about the function of the graph. So if we look at this, yeah, so let's actually go ahead and just plug in n plus 1. So n plus 1 squared over n plus 1 squared plus n plus 1 plus 1 n squared plus 2n plus 1 over n squared plus 2n plus 1 plus n plus 1 plus 1. All right, we're going to get n squared plus, we're going to get 3n plus 3. All right, so looking at this, so far we don't really actually have a good comparison between these two. That's super obvious, but we can also look at this, and if we think about this, our denominator is going to grow faster than our numerator is, because we have the same power on both of them, it's just we have more on the bottom. So therefore, we can go ahead and just by that logic say it's decreasing. So let's also go ahead and try to take our limit. So what we're going to do is let's go ahead and just divide by n squared on both the top and bottom. So n squared over n squared is 1. N over n squared is 1 over n. 1 over n squared is plus this 1 over n squared, so that's 1. So we can see we do not fulfill that second one. So what we can do now is we can plug this in to our test for divergence. Just to fully prove it, so -1 to the n squared over n squared plus n plus 1. We're going to get does not exist. So therefore it diverges. All right, so let's do one more example. This one we have -1 to the n times the cosine of pi over n. All right, so the first criteria that we need to do is see if we're going to be increasing, see if we're decreasing or not. So for this one, what I would actually do, once again, you can graph it, and this one is actually pretty easy for us to go ahead and plot points. So for this one, what we can do, let's do cosine of 1. Yeah, where n equals 1 is going to be pi over 1, which is -1. Forgot to draw our little series in there, but there we go. Cosine of pi over 2 is 0. Cosine of pi over 3 is going to be 1/2. Cosine of pi over 4 is square root of 2 over 2. So it looks like that we're going to actually be increasing on this one. So we're already don't meet the first one. It's not, we can just say it's not applicable from here. But if we wanted to go ahead and just fully prove that, and just kind of, you know, fully prove it, if we took our limit as cosine of pi over n, that's going to essentially get us cosine of 0, which is 1. So therefore, that one doesn't match either. So we can say for sure that it diverges. All right. So let's go ahead and just briefly talk about estimating sums before we go. Estimating sums with alternating series test, with alternating series. All right, so we have our alternating series estimation theorem. And it states that if our actual sum is equal to the summation as n goes from 1 to infinity of -1 n minus 1 b to the n, where b to the n is greater than 0, is the sum of a convergent alternating series, then the absolute value of our remainder is equal to, which is essentially, once again, our partial sum minus our actual sum, is less than or equal to b to the n plus 1. All right. All right, so what we're going to go ahead and do is we're going to go ahead and do an example. So what we want to do is we want to go ahead so the first thing we're going to do is we're going to go ahead and compare Sn and S, or well, in this case, the 100th partial sum, and C is kind of look and see how well that approximates the series, n equals 1 to infinity of -1 to the n minus 1 over n. All right, so if we look at this, we know that if we go scroll back up, we know that the absolute value of our remainder has to be less than our b sub n. So in this case, our b sub 101. So therefore, r sub n is going to be less than 1. So in this case, if we pull out our b, we're going to get -1 to the n minus 1 times 1 over n. So 1 over 101. So, and that is going to be approximately, if you put that into a calculator, 0.0099. All right, so if we want to go ahead and actually find the actual sum, so if we go ahead and plug in our actual sum into a calculator of our initial series, so our -1 to the n minus 1 times 1 over n, that's going to be equal to the natural log of 2. And our partial sum, if we plug that into a calculator, is going to be equal to 0.6 688,172. And then if we take the difference of that, that is going to get us 0.004975. So we can see that that does hold true. Our actual error is smaller than our estimated error. So that is actually all that I have for today. I know both of these tests are pretty simple. I know the next upcoming ones are a little bit more time consuming and difficult, but you know, we can go ahead, we'll work through these. And with that being said, I will see y'all next week.